Rising from the boundless embrace of the cosmos, stars ignite the space with the festive glow. At the heart of the galaxy, a mysterious door opens. A colossal black hole cradles the world in enigmatic light. Stars dance, exploring the infinite cosmic forest. Their birth and death weave a mysterious song buried within us. In the tranquil cosmos, the silent dawn of the future, unfolding mysteries of black holes at the center of the galaxy. Here, the melodies of stars and the scent of black holes blend as time in the universe flows like an endless celebration. Subscriptions, likes, and notification settings empower video creation. Today, in the fourth session of the Introduction to Astrophysics, we delve into the birth and death of stars, the formation of planets, and the mysteries at the center of galaxies and black holes. Birth of stars, accumulation of molecular clouds. Stars are typically born from massive structures known as molecular clouds, composed of gas and dust. These clouds undergo initial stages as the most dense regions accumulate due to the force of gravity. Triumph of gravity. The accumulated material, compressed by gravity, experiences a rapid increase in temperature and pressure. Near the center, nuclear fusion begins, marking the birth of a star. Hydrogen fusion. Primarily, hydrogen undergoes fusion inside the star, transforming into helium and releasing tremendous heat and light. These fusion reactions maintain the star's stable state, completing the process of star formation. Life and death of stars. Main sequence stars' life. Hydrogen depletion. Main sequence stars typically sustain nuclear fusion, converting hydrogen into helium. As hydrogen is depleted, helium synthesis begins. Red giant phase. With helium fusion initiation, the star expands significantly, transforming into a red giant. Fiery demise. Helium-rich shell. Separation. In the red giant phase, as the central helium depletes, the helium-rich shell separates. The core becomes more compact, evolving into a white dwarf or neutron star. High-mass stars' life. Hydrogen depletion and supernova explosion. High-mass stars, having more mass, undergo rapid hydrogen depletion. Helium fusion progresses through various stages, culminating in a supernova explosion. Formation of neutron star or black hole. After a supernova explosion, the remaining central part transforms into a neutron star or a black hole. Stars follow diverse evolutionary paths based on their mass and characteristics, concluding their lives by providing our universe with various chemical elements. Formation of planets. Protoplanet formation. Within molecular clouds, formed along with stars, protoplanets exist concurrently with the birth of stars. These protoplanets, accumulating dust and gas, grow in mass through gravitational attraction. Protoplanets represent the initial stages of planets formed in the process of planetary formation. As material gathers in a disk around a star to form planets, protoplanets are the early stages that form within this disk. Protoplanets form as dust and gas gather under the influence of gravity, growing into planet-like shapes. Subsequently, they can evolve into larger planets with more mass. Protoplanets serve as intermediate stages in the process of celestial formation, growing through collisions and mergers due to gravitational forces. These protoplanets can later evolve into larger planets by attracting surrounding material or by collisions and mergers of gas and dust, forming larger celestial bodies. The formation of protoplanets plays a crucial role in understanding the initial stages of planetary systems. Collisions and mergers of protoplanets. protoplanets collide or merge as a result of gravitational forces, forming planets. During this process, continuous collisions lead to the dispersal of dust and gas around the planet, influencing the later formation of satellites or the planet's environment. Angular momentum and gravitational collapse. Formed planets attract surrounding dust and gas, creating expansive atmospheres. Simultaneously, gravity shapes the planet's structure, forming its interior through compression and heating. Celestial identity and accretion. Interstellar dust and gas surrounding planets contribute to their identity and composition. Planets absorb interstellar dust and gas, shaping their unique characteristics. Planetary migration. Some planets can move away from their initially formed positions and migrate to different orbits. This phenomenon is called planetary migration, and it significantly influences the dynamic evolution of planetary systems. Planets possess unique environments and characteristics, and the diverse processes and features associated with their formation contribute to the richness of the universe. Round shape formation. Principles of stars and planets. Result of rotational motion. The primary cause of stars and planets having a round shape is the initial rotational motion. Before the formation of stars and planets, there exists rotating material in the form of molecular clouds or rotating disks. Conservation of angular momentum. The initially rotating molecular clouds or rotating disc-shaped material continue to rotate due to the conservation of angular momentum. This conservation of angular momentum causes newly forming celestial bodies to also rotate. Rotation around the axis of symmetry. When rotating material rotates in a specific direction, the action of gravity causes this material to continue rotating around an axis parallel to its rotation. During this process, the material compresses toward the center, taking on a spherical shape. Disk formation. As rotating material converges toward the center, mass accumulates at the central region, while the remaining material surrounds it in a disc-like shape. This disc continues to rotate, eventually leading to the formation of a star or planet at the center. Balance of gravity and pressure. The object, star or planet, formed at the center is compressed by gravity, but simultaneously, internal pressure reaches equilibrium with gravity. This balance maintains a spherical shape, allowing stars and planets to evolve into celestial bodies with a round shape. This process explains how stars and planets acquire a spherical shape due to the dynamic influence of initially rotating material in their early stages. When a star dies and forms a black hole, the surrounding planets can also be drawn into the black hole. Black holes possess an extremely strong gravitational force, capable of absorbing objects in their vicinity. This occurs within the event horizon of the black hole, and beyond this point, objects disappear into the black hole and are no longer observable. The process of surrounding planets being absorbed into a black hole unfolds as follows: stellar collapse. When a high-mass star exhausts enough hydrogen, gravity overwhelms the core, leading to the collapse of the star into a black hole. Formation of black hole. The collapse of the star into a black hole creates an extremely dense point at the center, forming the event horizon of the black hole. Absorption of surrounding planets. The black hole, through its strong gravity, absorbs nearby objects, planets, and gases. As these objects pass through the event horizon of the black hole, they vanish into the interior. Relentless gravitational pull. Black holes possess an endlessly strong gravitational force, pulling nearby objects towards themselves. In this process, planets are torn apart by the gravity of the black hole and are drawn into it. This brief explanation describes the process of a black hole absorbing surrounding objects. When a star collapses into a black hole, what gets drawn into the black hole depends on the mass and characteristics of that specific black hole. As a black hole absorbs surrounding objects, its mass increases. However, the growth of a black hole is not infinite due to the phenomenon known as Hawking radiation, proposed by Stephen Hawking. A black hole can lose mass. Increase in black hole mass. Absorption. Black holes absorb surrounding objects through gravity, leading to an increase in mass. This is a result of the strong gravitational pull of the black hole. Inflow of matter. Matter from distant regions of the universe can flow into the black hole and be absorbed, contributing to an increase in the black hole's mass. Decrease in black hole mass. Hawking radiation. Hawking radiation. Stephen Hawking proposed that black holes emit radiation due to quantum effects near the event horizon, leading to a process called Hawking radiation. This radiation causes the black hole to lose energy, resulting in a decrease in mass loss, and energy emission. Particles emitted through Hawking radiation reduce the mass of the black hole. This implies that if the mass loss due to Hawking radiation surpasses the mass gained from absorbed matter, the black hole's mass will decrease. Ultimately, the growth of a black hole is determined by the balance between the absorption of surrounding matter and the mass loss due to Hawking radiation. Within a black hole, gravity is extremely strong, causing time to be distorted and even appear to stand still. This phenomenon is known as time dilation or time distortion. Time distortion in a black hole near the event horizon. The event horizon is the surface of a black hole, and entering it leads to time distortion due to the influence of gravity dependent on gravity strength. As gravity intensifies deeper into the black hole, time distortion becomes more pronounced. Time stands still, passing beyond the event horizon into the interior of the black hole, results in an infinite increase in gravity, causing time to nearly stand still. This means that for an observer outside the black hole, the movement of objects near the event horizon appears slowed, almost frozen. Hawking radiation's impact. Hawking radiation is also influenced by gravity, and the energy of particles emitted from the black hole is related to time dilation when observed by an external observer. Time distortion in a black hole is a phenomenon derived from Albert Einstein's general theory of relativity and occurs in environments where the gravitational field is extremely strong. There is a possibility that a massive black hole exists at the center of a galaxy, although observing this region is generally challenging, making it difficult to obtain precise information. However, it is a common astronomical inference that many galaxies include a massive black hole at their center. Possibility of a black hole at the center of a galaxy. High-density environment. The central region of a galaxy is characterized by a high density of stars, gas, dust, and other materials. In such a high-density environment, the accumulation of substantial mass towards the center can lead to the formation of a massive black hole. Central activity. Active galactic nucleus, AGN. Some galaxies exhibit phenomena known as active galactic nuclei, AGN, at their centers, emitting high-energy radiation. This could be explained by the gravitational acceleration of surrounding material near a massive black hole. Orbital motion of stars. Observations of stars rapidly orbiting at the center of a galaxy can be indicative of the presence of a massive black hole with a strong gravitational field. These observational clues suggest the possibility of a massive black hole at the center of a galaxy. However, obtaining accurate information is challenging due to the difficulties associated with direct observation. Whether there is a massive black hole at the center of a galaxy is still not definitively answered. However, based on current research and observations, it is estimated that most galactic centers likely contain a massive black hole. The central region of a galaxy is a high-density area, making it conducive to the growth of a massive black hole. Our own galaxy, the Milky Way, has been observed to have a black hole at its center in 2019. Nevertheless, not all galaxies may have a black hole at their centers. Black holes are known to form under specific conditions, and galaxies that do not meet these conditions may not host black holes. Therefore, it cannot be assumed that every galactic center contains a black hole. The idea of a massive black hole at the center of a galaxy has been theorized since the early 20th century, with evidence emerging in the 1970s. If a black hole exists at the center of a galaxy, it was predicted that radiation emitted as surrounding material falls into the black hole could be observed. To detect this radiation, scientists have studied the central regions of galaxies. Notable scientists who contributed to this research include Reinhard Genzel and Andrea Ghez, who received the Nobel Prize in Physics in 2020 for their work on observing the motion of stars near the center of our galaxy. Reinhard Genzel, a German astronomer, measured the motion of stars near the center of our galaxy since the 1990s, concluding that a black hole with a mass equivalent to 4 million times that of the Sun exists at the center. Andrea Ghez, an American astronomer, independently studied star motions in the galactic center, estimating the mass and size of the central black hole. Both Genzel and Ghez were awarded the Nobel Prize in Physics in 2020 for their contributions. Stephen Hawking, a renowned British theoretical physicist, contributed to the understanding of black hole thermodynamics. He proposed the concept of Hawking radiation, suggesting that black holes could gradually evaporate by emitting radiation. Hawking authored several books on black holes and the origin of the universe. In conclusion, the presence of a massive black hole at the center of galaxies is inferred from various observations and research, with notable contributions from scientists such as Genzel, Ghez, and Hawking.